I have to let you in on a little, it's not a secret. I am making a collection of short videos. I've already made the first 5 of these. And I've started to post them, but I ran out of time. But by tonight, I'll have made 6 very short videos on these topics. The reason that made me think of it is because one of the questions I'm going to do when I'm analyzing functions is the 2023. So I'm trying to kind of hit these things again. So even if I don't, whatever I do today, there will be later tonight, and I'll put this on the discussion board, 6 short little things on this. I've already posted the first 3. But I've already made the first 5, but this will be very informative. So I'm glad that you're all joining me so that we can fill in a few pieces. So Sasha has a question on this. So this is kind of more of the way I would ask it in a regular calculus course, which is we've got some weird function. We would like to know a bit about it. And I would say the most common thing we want to know about it is where are the max and min, the high points, the low points, all that stuff. So the moment we see this, the words critical values or the word max or the word min or the word horizontal even, we do the following things. So what do I need to do? I will record this. The link to Zoom you sent in the first email might be different than this one. Uh-oh. Darn it. Well, shoot. Thank you for telling me that, Donalda here. So while I'm thinking about that, take the derivative and set it equal to 0, anybody that's on here. And then we'll talk about the classification part, which is your question. I am going to do one maneuver here. I have made this mistake before. I was hoping I was done making this mistake where I make the link in 2 places. But we'll have time here. This is an old ed discussion. No, here. Zoom link. This is the one that worked, I think you're saying. You're going to see everything here. Let me double check. That's an old. 1 second while you're still working that one. Oops, somebody's unmuted, which doesn't bother me, but you might not want us to hear what you're doing. Oh, they're still, I better mute them before they get themselves in trouble. Just a sec, I'm going to check this link I sent out. 8, 9. Darn it, darn it. 8, 4. Correct. Zoom link here. I want to get us going, so great. I think that's the one we're on now, 8, 4. So hopefully that gets us a few more here. I feel like maybe I should restart the Zoom link. Okay, so let's go here. So we have f prime of x, and we can go longer. We don't have a time limit here. Apologies that I didn't get that. I was hoping I could make an announcement about one tomorrow, and then I looked at my schedule tomorrow, and I don't have a window of time that I can fit. I have a band concert late into the evening. I have meetings throughout the day, so I just couldn't fit it. All right, so this will be good though. So this one I think does factor 2 numbers that multiply together to give me, I'm guessing it does because it's on my test, and 2 numbers that add together to give me 2. But the quadratic formula would be fine too. Negative b plus or minus square root b squared minus 4ac all over 2a. So it's going to be negative 2 plus or minus square root of 36. So what 2 numbers? I'm going to also factor it. I like to let's do it both ways here. I think it's going to be 4 and negative 2. So x plus 4, x
Got,
minus 2.
I got -4 and 2.
Lovely. Yeah, sorry. The factors will be x plus 4, x minus 2. And when you solve, you'll get x equals -4. So we're saying the same thing. That's great.
Yeah.
Good, good. So the two, at that point, we know, one of the real powers of calculus is even without graphing this, we now know that there's two bumps, possibly. So let's do that final analysis just to figure out, because the truth is all this tells you is the slope is 0. There's actually 4 ways your slope can be 0. So here's kind of overkill explanation is we don't know yet which one of these 4 things we're dealing with. I'm writing over here on the left of the screen here. So we don't know which one of those we're dealing with. But if we knew a bit about the slope, we could figure it out. And so that's the next step I do is I figure out, I go over here to -4, I write a 2. This is how I like to organize it. Down here, I'm going to write what's going on with the slope. And then up here, I'm going to summarize what that means for the height. So my goal is to put arrows in each of those. What's happening as we go left to right? So let's take our time here and kind of summarize. Any other question about the solving? I'll go back. I saw there were a couple other comments, but I'm just going to finish this question, then I'll see what I missed in the chat. I'm just going to erase that for a moment. Well, maybe I shouldn't have done that. I've got space. Let's just make it bigger. Boom. Over we go. Okay, so let's hit this analysis piece carefully. So at this point, we know that the derivative is x squared plus 2x minus 8. We also know we can factor it. There's a certain reason I'm writing that. But both of these are going to be fine for what we're about to do. And we think of that as slope. If you have a positive slope, it means you're going uphill. And if you have a negative slope, it means you're going downhill. We actually know, let's say this first. At -4 and 2, just so to give everybody a chance to blow up the chat, what is the slope at -4? And what is the slope at 2? This is a very quick thing, a number you can type in. And I will post this later when I have it. We're on Sasha's question. I'm reading back through everybody. It's 0, yeah. The slope is 0. In fact, that's what we did back here, right? I've had a few people say, do I plug this into the derivative? Well, you could, but you should already know that it's 0 there. That was the whole point of this step. This step was to find when the slope was 0. And when you're on a bump of a graph, the slope is 0. Okay, so we already did that piece. Those are the only places where the slope is 0, because if there had been more, we would have found them when we were doing the solving. So now I'd like to think about what happens if I'm less than 4. So let's take a number smaller than -4. Will the slope always be a 0? The slope will always be 0 at the critical values. In order for it to be a critical value in this course, the slope has to be 0. That's what a critical value is. It's a place where the derivative is 0. So if you had just a visual thing here, and this is great. This is something, so if you're joining me and this is too slow, this is something I'm going to do in a Zoom review. We're going to take our time, kind of hit some of these things. And we'll do a lot of this before the final. But these places right here are the places where the slope is 0. So if you ever want to find those, your job is to take the derivative, set it equal to 0. I feel like a lot of questions in calculus boil down to the understanding that the original function is the height. The first derivative is the slope. Yeah, please. Somebody raise their hand. Do you have a follow-up question before because we still have the analysis to do. I'm just hitting a few things. Oh, the hand went away. Okay, so now I'd like to know, we know where the slope is 0, but what about over here? So give me a number less than -4. And I would like to know when you plug that number into this, whether the slope is positive or negative. So how about -5 for lack of originality? So my question is, if you plug in a -5 here, and here, what do you get? I would prefer to plug it in here and here because it's just easier for me. Because the goal is not to get the number. The goal is to figure out if it's positive or negative. So let's do a little race. Oh, we have 33 of us. Thank you so many of you for joining me. We're just going to do problems. I'll record and post this later. For anybody that just joined, I will be posting a collection of review videos, which I've already made most of them. I just haven't had time to give them timestamps so they're easier to use. So I need to do a bit of editing, and those will be up by probably within an hour after this is done. But it's time for some calculator work here. How can I share this? Advanced. Is that going to cause a problem? It might. I don't have a good way to show my calculator. I can't do a Zoom review tomorrow afternoon as I'd hoped. That's why I decided to announce one tonight, because I have a meeting from 2 to 3:30, and then I have a band concert to be at in Ballard at 6. And it's too tight of a window for me to get in front of a computer. So sorry, Michelle, I can't do it tomorrow. But is this positive or negative when we plug in a -5? And when I do it, I just think about the factored form is really nice because I can see that this is going to be negative and this is going to be negative. Now you can actually compute the number, it's +7. But the important thing is it's positive. You could also just have plugged it into the original one and we would have gotten, what would we have gotten? We would have gotten, plugging in a -5 here is 25. Plugging in -5 here is -10 minus 8. I also see that's positive. So if the derivative is positive, that means everywhere before -4, it's positive. Because if it ever changed, it would have had to have been 0. And -4, it's the first time it's 0. So then I draw uphill. From left to right, it's going uphill. So this is the key moment. This is where you have to slow down in your work. The rest of this will be quicker. Okay, now I'd like to plug in something between -4 and 2. We'll get to that, Giovanni. Hold your, or ask me that question again if I miss it in the chat later. Somebody's asking me a question privately. Sometimes when the chat blows up, I forget a question. So if I don't get to it, let me know. Okay, so what's the value between -4 and 2? Try to fill this piece in. What's something you could plug in? Basically, I just would like to have I'd plug in 0 too. If I plug in 0, do you get a positive or negative? So I want to know whether I'm going to put a minus or a plus here. So give me a minus or plus in the chat. Negative, lovely. Downhill. Great. One more to do. Plug in something bigger than 2. So this is probably, there's a couple moments that might be slower if you're doing a test question and you don't have it factored, or you are taking some time. It's back to positive. So I would plug in, I like to plug in a really big number like 100, something that really convinces me that that's a positive times a positive. So it's uphill. So I'm kind of the belief that once we draw that number line, we've answered every question that could be asked. If the question was asking about increasing or decreasing, we'd have the answer. But this particular question was just asking where are the max and min. And this is why I like the arrows so much, because for me, it's really easy to see that that's going to be a local max and that's going to be a local min. In fact, I have a sense of what the picture looks like now, which is really what I want students to take out of the calculus courses. That thing goes up and down, and this little dot is going to be when x is -4, and this spot is going to be when x is 2. Yeah, so we would say the critical values are -4, and we would say it's a max, and 2, and we would say it's a min. It's a maximum if it switches from increasing to decreasing at that point. So this is a max. It changes from uphill to downhill. And that's the point of figuring out these positives and negatives, because they tell us if it's going uphill or downhill. And the minimum is a place where it changes from downhill to uphill. How are we doing on that one? In this case, there's no horizontal point of inflection. That's this other situation here. And if that were the case, we would have had a picture where, I don't want to mess up our nice number line. If we had a picture where it switched from increasing to increasing again, then that would be a horizontal point of inflection because you're switching from increasing to 0 to increasing. So if I wanted to do, I think horizontal point of inflection appeared on homework. It wasn't a major emphasis because we did point of inflection, but if you sort of did a comparison test here of the, yeah, Sasha?
Yeah, sorry. Also on the solutions page for spring 2023, you
Yeah.
show work for the second derivative and when it's concave down and concave up, but the
Uh-huh.
question isn't particularly asking that. So would we have to show that, or is it fine if we just end it with the local max and local min?
Yeah, great question. You can just end it, but let me see if I can locate. Can you see the browser?
Yeah.
Okay, good. I have to select the windows that are visible. So old exam, this one. Sometimes is it this one?
Yeah, like under the number
Oh, I
line,
see.
the second.
Yeah. That was like a confirmation. So the only reason I wrote that, yeah, I would not expect anyone to do. Oh, part of the reason I wrote that is I think some students did it that way, and I wanted to write enough when they went to grades because maybe they. But this is another way to get this information. Second derivative is kind of it gives a little more information, but it also confirms what we're seeing. So quick visual with my hands. But if you have a place that you know the slope is 0 and it's concave down, then you know it's a maximum. So this information, let's see if I can use the annotator here. This information is also given by the fact that it's concave down. If you know the slope is 0 and you're concave down, you're at a max. If you know you switch from increasing to decreasing, you're at a max. So if you had time on a test and you had already figured out, you're pretty sure it's a max, you could also compute the second derivative at -4 and see if it's concave up or concave down. Similarly, we would expect this one to be concave up. So this was a confirmation, but also was I was writing. I try to write my solutions in as general a way to sort of answer some of the questions I get. Um, so yeah, you do not have to do that. Your solutions do not have to be robust like mine are. They should be minimal. There's no reason to do more work. So that's a good question. Thank you for that. All right, so there was a question about integral problems with bounds. Love it. There was a question about average cost. So I'm going to just make sure I didn't miss anything. Okay, so a question about average cost from winter 2018. And then next, and I tried to, oh, the annotations are still there. Be gone. No, that didn't work. I think I could do this. Delete all drawings. Wonderful. I want that to be gone. Bear with me here. So we did spring 23. This is just kind of helpful for me. Page 2B. And then we did, and that was recorded. I think that's when I hit record. So this will be posted later. And then we did spring 23 2A. And now we're going to do winter 18 to exam 2, question 3, C. I don't recognize that type of problem. So that's good. We'll go look and see. So it's sort of a what in the heck's going on there. And then I had a question. I'm just going to collect some questions here. Because not everyone was on at the beginning, I didn't get to have my normal start. We have a question about definite integrals, meaning integrals with bounds. If at any point my sound kicks out, just let me know in the chat and I'll switch mics. In my last review session, this mic went out for a moment. How to know if a function has a point of inflection. So there's a question about point of inflection. Quick answer to that is there's a little technicality. You do need the second derivative to be equal to 0, but it's supposed to switch concavity. Now, I don't think we have any natural examples where this happens, but I'm just going to make something up. So if you went positive, negative, positive, positive, concave up, concave down, concave up, concave up, which is technically can happen, we wouldn't call 5 a point of inflection. This is just to answer. There's a private question about this. We wouldn't say this is a point of inflection because technically it didn't change there. But let's try to find one of those questions in a bit. So I'm going to look at winter 2018. Then we'll try to do something with definite integral bounds. The bad part is you can't see each other's comments. I've been trying to think of how to switch, like we should do a Twitch stream or something, but I'm not knowledgeable enough to do that. Okay, winter 2018 midterm. And somebody suggested maybe we look at finals too, simply because it gives us something that maybe nobody's looked at yet. So maybe if we run out of things, we'll look at that. Winter 2018. It's kind of nice to look. And I made a video where I went through all these. This is part of, I separated. I made a video where I did the derivatives from all my old tests. Then I made a video where I did definite integrals, indefinite integrals for all my old tests. And then I did a video where I did all of these. That's coming out. They're all short videos, but you'll see that in a bit. So the question is asking about one of these. What was that question again? Sorry if the person's already left. Giovanni, I think you were asking about winter 2018. Did I click on the right one? Yes. Then it was question 3C. Gotcha. Thank you for that. I have asked questions about average cost before. Let's say a couple things about this and sort of take what we can out of it. So in this question, the bad part about this question is it kind of builds on the previous parts. So I might ask it a slightly different way, but so before we get to the other parts, I need something from earlier. And since I need something from earlier in the problem, let's talk about a couple of the parts from earlier in the problem and then get to that last part. Okay, I got my chat ready. So how do we do these pieces? This is a particular skill, I would say. And I've already made a video about this skill as well. This is what I would call the plus C skill, the constant of integration skill. I guess the first question is, how do I know that it has to do with integration at all? But they gave me the derivatives. The marginal revenue is the derivative of total revenue. So I should realize that, hey, they gave me the derivative is this. And they also gave me the derivative of total cost is this. And then they're asking me for these formulas. So we need to do an antiderivative. You don't even have to write the integral notation, but you have to realize it's an antiderivative question. So take a moment and write what you think those are. And then we'll talk about the plus C part of it, but let's separate these pieces. So we need to do antiderivative or integrate, antiderivative and integrate. And we are going to need to remember a couple of our rules. One of them is this. The other one is this. I'll just write these over here for reference. Okay. And if it was me, I probably would have a calculator handy as I'm doing this one because I need to write the following. So we need to do 1 over A, but 1 over A is this 1 over 0.02 plus C. So I'm really tempted to do 7 divided by 0.02. And sorry, I don't have I have a camera that I can put on my um, calculator, but I'm afraid if I set it up that the zoom will go out. I'm afraid to do it. So 7 divided by 0.02, I got 350. So this is 350 e to the 0.02 cube plus c. And one of the most common questions I get is this c, but that's just the integration step. So let's do the other integral as well, and then we'll talk about the constants. Are we good with this integral? Do you want to give me a thumbs up if you have it? Okay, I see 1 thumbs up. 3. Somebody's asking about the antiderivative step for E. I can talk about that in a second. Oop, I have an X. Oh no. So a question about this piece here. So let's talk about 2 things. I get what you're saying. So the derivative, I'm going to use this notation here. Just, well, maybe I shouldn't. I don't want to throw people off. So let's just use a prime for the derivative. So imagine I put a little prime here. I say, I want to take the derivative of what's inside of here. And let's do e to the 4x. So we have a certain rule for that. And then separately, I would like to talk about the integral of e to the 4x. And we have a certain rule for that. I think there might be the question I'm being asked privately in the chat might be about a confusion between those two. One of them we multiply by 4 because of the chain rule, and one of them we divide by 4 because we're trying to undo the chain rule. This one is e to the 4x times 4. This one is 1/4 e to the 4x plus c. And the reason there's a 1/4 is because if you went to check your work and take the derivative of this, you would need to use the chain rule. And if you use the chain rule, there's going to be an extra 4 here. But the original problem didn't have a 4, and that's why we had to put the 1/4 to cancel it off. So that's where that comes from. So the rule for the integral does have dividing by that number. Does that answer your question, Abigail? Yeah, so that's why the 0.02 is on the bottom there. Once you've learned derivatives and integrals, it's natural to make the mistake where you do a derivative when you should have done an integral or vice versa. So if you ever make that mistake, you're in good company because everyone's done that. Let's integrate this second one though, because I want to just talk about the plus C part in and of itself. So I'm going to do this one. These are all examples of this one now. So we're going to have power is going to go up. And really the way I think about it is the power goes up and then I worry about the number out in front. So we're going to end up with a q cubed. We're going to end up with a q squared, and we're going to end up with a q and a plus c. So this power is going to become a 3. This power is going to become a 2. This power is going to become a 1. And there's going to be a plus c. And so then it's kind of a similar thought process. We're trying to undo the number that would be out in front. So there needs to be a 1/3 here. Because if you check it and take the derivative, there'd be a 3. So we're trying to kind of undo. This one, there's going to be a 1/2, but it's going to be a 12. So what number goes right here if you're still awake? We had somebody in lecture today that was full on asleep when I was handing out the review sheets. And I said to the people next to him, do you think he wants a review sheet? And they said, yeah, we better leave one there. Okay, so we're going to divide 12 divided by 2 is 6. Yeah. And the last one's 124. And there we go. That's the integral step. I know we've taken a long time to get to the original person's question, but that's the integration. You don't have to use the integral sign. You just have to know that's what we're doing. Okay, so now the next piece is the plus C part. And that's why I was kind of saying this question is really about the plus C, which you now know is going to be the start of the third page of your exam because of what I said today. So you might have something similar. I'm not saying it's the same functions, but similar in structure. So the real question is, what is that and what is that? So now we have to think, don't assume anything about those values. Just look at the information. So they told me that the total cost at 0 is 15. So that's what it means for the fixed cost to be that, but it also reminded us that's what it means there. Now over here, they didn't tell us the initial value, but we know what it is. The total revenue at 0 has to be what? So this is a fact you have to bring with you into the test. What is the total revenue at 0 equal to? Sorry, I should be muting my mic when I'm drinking. It's bad mic etiquette. Total revenue at 0 is 0. Now, the big thing here is that does not mean C has to be 0. You always have to plug in the X and the Y. That's the biggest takeaway from this. So now let's do it. Let's plug in the X and the Y, meaning this side should be 0 when we plug in 0. So 350. And I'm just going to write E to the 0 because 0 times 0.02 is 0 plus C. That's what that's telling me. What is E to the 0? E to the 0 is 1. So we get 0 is equal to 350 plus C. So C has to be negative 350. And the thing we're going to write here is 350 minus 350. It looks funny, but the way you check your work is you could take the derivative of this and you would plug in 0. There's two things to check. So if you plug in 0, you have to get 0. So you could check that. And when you take the derivative, you have to get what we started with. And both those things will work out because 0.02 times 350, I bet is going to be 7. So that'll check out. And when you plug in 0, you're going to get 350 minus 350, which is 0. So that's really what we're after, is find a function that has these two properties. And we've done it. Okay, the other one's a little tamer in terms of plugging in. This one says when we plug in 0 here and plug in 0 here and plug in 0 here, what needs to pop out is 15. So you get 0 minus 0 plus C has to be 15. And so C has to be 15. And so we get this 1/3 Q cubed minus 6Q squared plus 124Q plus 15. All right, so that's the plus C piece that you were doing in the 12-4 homework. We good there? Questions on that? I bet we could find more of those in a few places. The question being asked was about the last part of this question. We can go back and do other things, but it was asking about this. Now, I think if I asked something about average cost, what's challenging about it, what's challenging about grading a question like this is if a student messes this up, then they're not going to be able to do this part. In recent years, I try to avoid that as much as possible because it makes the grading sad. So I would separate them and probably just tell you the function. So let's change this question to kind of my modern way of asking this. What if I told you the average cost was the following? 1/3 q squared minus 6q plus 124 plus 15q. Now that's what you get if you divide total cost by q. But let's assume for a moment, I'm trying to state this in a way that's more like something I would ask on your exam this Friday. If I gave you that function and then I said, when is it concave? Is it concave up or concave down or neither when q is 1? So at that point, it doesn't matter that it's average cost. It doesn't matter what it is. It doesn't matter what the name of the function is. It could be the Andy function. It could be the TQRZW function. It doesn't matter. We're being given a function and asked if it's concave up or concave down at 1. So how do we do that? So this goes back to this idea of if you have a function, we think of whatever the function is we're studying as the height. We think of the derivative as the slope. That's what it represents, slope of the tangent line. And the second derivative is the concavity. So really everything goes back to these three things. So if a question is asking me if something's concave up or concave down, they're asking me about the second derivative of whatever we're talking about and whether it's positive or negative. Okay, with that being said, what do we do in this question? What would be your next step if you were taking this exam? I know I'm asking questions that are hard to type an answer to. What do we need to do? Take the second derivative. Yes. So we need to start taking derivatives. Now, before we can take derivatives, calculus students don't like this. You could use the quotient rule, but that's going to be miserable. So we'd rather write this as 15q to the negative 1. So that's part of those little maneuvers you need in order to use calculus. You need enough algebra that you can write things in a way that we can use our rules. Okay, first derivative. So now I'm just on a mission. The moment I saw this word concave up or concave down, I was on a mission to find the second derivative. So this is going to be q, this is going to be minus 6, this is going to be 0, 15q to the negative 2. Okay, that part's done. Let's do it again. Second derivative, 2/3 minus 0. So minus 0 plus 0. You don't have to write all the zeros. I'm just explaining what I'm doing. And then what's the next number that's going to come out of my pen here? What's the coefficient I'm going to get? Just to check in. It's a number. The negative 2 will come down and it will become 30. Yeah, lovely. Q to the negative 3. Even better. Yep. People are telling me that in the chat. Okay. So what's this about? And there's a small comment I'd like to make here is I don't like negative exponents when I'm trying to analyze something or plug in. So my preference, this is not something that's required at all. But for my own thinking, I like to rewrite this as 30 over q cubed. Because I know I'm about to think about it. And for some reason, that's just easier for my brain to think about than q to the negative 3, in my opinion. So now that we go back to the question and it says at 1, is it concave up or concave down? So we actually don't have to set anything equal to 0 at all. They're asking us for a very particular thing. If we wanted to know the height at 1, we'd plug it into the original function. If we wanted to know the slope at 1, we'd plug it into the derivative. And if we want to know the concavity at 1, we'd plug it into the second derivative. So this question was really asking you to plug 1 into the second derivative. So we put a 1 in here. We put a 1 in here, put a 1 in here. And actually the question wasn't even asking you to plug it in. It didn't even ask what the number was. The number actually is 2/3 plus 30 is what it would be, or 30.6 repeated. I don't care what that number is. I just want to know what that number means so that I can circle the correct thing here. The reason I know I have to plug in 1 is because what the question asks. So the question says, is it concave up or concave down? Particularly at 1. So that actually makes the question a little easier. If the question said to find the interval where it's concave up or concave down, then you would set the second derivative equal to 0, which we could do. But if it's just asking you what's happening at a particular number, then there's no reason to have to do that. Yeah, good question, Giovanni. So I know that it's positive at 1, so it's concave up. But if we want to do the full analysis of tell me everywhere that it's concave up and concave down, then we would do the following. We would take the second derivative, set it equal to 0, solve. If I had to solve that, I'd multiply everything by q cubed. Actually, I'd also multiply by 3 because I don't like fractions. And then I'd multiply everything by 3, so it'd be 2q cubed plus 90. Oh, that gives me like a negative number. So that was certainly not the intention. It's some messy number. The cube root of negative 45. And you could draw your number line. And somewhere over here is the cube root of negative 45. And I suspect it's positive on this side and negative on the other side. But that's overkill because the question did not ask us to do the full analysis. It just was saying what's happening at 1. I don't know, 1 somewhere over here. If it was 0, you would say neither. Yeah. Yeah, this is the sufficient work to do this. You take the second derivative, plug in 0, plug in 1, and stop. And circle concave up. So this is AC double prime of 1 is positive. It's positive because the second derivative, it's concave up because the second derivative is positive. I think the reason I said that, and I might say it differently now, somebody's asking about why did I say show appropriate derivatives? Because sometimes what I see when I go to grade a question like this is someone randomly circles 1. And so if they don't give any work. So the reason I would make a statement like this is if somebody got lucky and circled the correct one, I wouldn't give them full credit. And I feel like if I don't give them a warning about that, then they might be mad at me. So that's what I was doing there, was trying to give a warning that if you do nothing and just guess, it's insufficient. But anyways, I can say a few. Somebody's saying, how is it concave up? We could run some kind of side experiments, but I know there was a question. The next on the docket was, yeah, so just briefly, so we're gonna talk maybe about doing something with a definite integral in a moment. I do want to point, yeah, if the second row is positive, it means it's concave up. But I do, since some people joined later, so in a moment, this is the beginning. Yeah. This is the beginning of this series. There's going to be 6 short videos. I've actually already made 5 of them. if you click on this video, it takes you and you open it. Oh no, we're gonna hear this guy. We don't want to hear the guy. At the end of each video, it automatically takes you to the next one. I know I'm pretty fancy with my stuff here, but at the end of this video, there'll be a link to the next one that comes up. I don't know. There it is. And so this one's already up, which is the part 1, where I just do some derivatives. I think I've also posted part 2, but it takes me a few minutes to post them, and I ran out of time. I was hoping to have them all up before this thing. So at the end of this one, there's the next one. So if you need practice with derivatives, that's already up. If you need practice with indefinite integrals, no bounds, I do a couple of, this is like a 3-minute video. So they're all kind of short. There will be 6 total where I do these different skills. That's something I've been doing for more of my classes. So I'm trying that here. So I wanted to separate this so that people could see where they're at. So this will all be up tonight. I think that was one of the questions being asked. I like to do that before reviews like this because I never am able to answer everyone's question. So I'm like, hey, there's more answers to come. Let's find something with a definite integral, perhaps. Maybe we can look at an old final. I don't know if that's a good idea or not. Winter 2019 finals. This is something no one's looked at. There's a derivative, there's an integral. Let's do all 3 of those. Any objection? A derivative, an integral, and a definite integral. And this will hit, I think, somebody was asking about a definite integral. This is the winter 19 final. Now, I'm not saying you need to go study finals. I'm just saying, I imagine everyone just probably glanced at the exam archive and maybe you're looking for something different. And since I'm already posting videos for all those, I'm getting bored with those questions too. So let's play the winter 2019 final. Date. I don't know what that means. Edwin, sorry. If you can find it, date for the exam. Yeah, winter 29. So you would go, one more thing just to direct. So if you go to my exam archive, it's right down here. I haven't cleaned up the final exam archive. I will add one more. But I would say if you just want to see some more problems, the only thing you have to be wary of is we haven't done multivariable problems yet. That's the last topic. But these have full solutions. And so if you just wanted to see a few more, I feel bad at it. One of the first people on was talking about that, and I was like, oh, that's a good idea. So let's try. So the game we need to play here, the commonality for all 3 of these is we have to simplify first. Yeah, this is the 2019 one from there. Winter 2019. Okay, so we need to do some rewriting. The rewriting here is writing 3 plus the log of 5t minus t to the 4th to the 1/2. Why am I using that color? And this is a derivative question, so we got to kind of get ourselves situated. It's a big, huge mess of stuff. When you have a big, huge mess, you have to think product, quotient, or chain. So to me, that doesn't look like a product. A product would be like a function with a t in it next to a function with a t in it. I don't see that. A quotient would look like this, a function over a function. It's a chain rule. Now, I think of all the chain rules the same way, but some students like you to split it into 3 possibilities. So one type of chain rule is blah to the n. Another type of chain rule is e to the blah. And another type of chain rule is log of blah. But that's basically our three rules. We really only have three derivative rules: x to the n, e to the x, and log of x. Those are our three derivative rules. And x to the n minus 1, e to the x, 1 over x. So we actually don't have a lot of derivative rules in this course because we don't do any trig. So we only have three. Everything else is about putting them together. Okay, so when I look at this, what I see is the following. Something to the 1/2. And so we have a blah to the 1/2 question. And so we do that the same way we would do an x to the 1/2. The chain rule just tells us how to adjust if there's something else besides x inside. It says take the derivative as you normally would for a 1/2 power. You would write 1/2 blah to the negative 1/2. So that's step one of the chain rule. And that involved the recognition of this is what we're looking at. And then the rest of the chain rule goes like this. It says, okay, do the derivative like you normally would. And then copy down whatever's inside. So in this case, what was inside was this huge mess. Put a dot. And now you're done with the part that has to do with the 1/2. So then what in the world goes here? So now we do the derivative of the inside. That's the rest of the chain rule part. So we have a new job. It's almost like you just do a full refresh. Now with practice, you don't have to really like completely stop and go have dinner and come back. You just now can see that you're doing the derivative of this, and you need to think about that as its own problem. And whatever you get out of that is going to go in this slot. So we're going to kind of refresh and ask ourselves, well, what is the derivative of this thing? Well, it's got two different things separated by a plus. But what the derivative of 3 is 0. So that's not so bad. So it's 0 plus, and now we're down to this. The same sort of thing, product, quotient, or chain. It's not a product, it's not a quotient. It's the log of blah. No balloon question on the exam simply because I'm confined by what I've said in class. But the idea is of going, somebody's asking a private question like that. So yeah, no balloon question simply because that, but there will be questions where you have to go from a derivative to an antiderivative. Okay, so back to this question. Log of blah, we do it the way you do a log problem, and the log problem is 1 over whatever it is. Again, there's really only 3 rules. And the chain rule tells you how to adjust those rules. So the next thing I'm going to do is however we take the derivative of a log. So I'm going to write 1. So it's 0 plus. I don't need to write that. 1 over. And now we're done with the log part. 1 over whatever's on the inside. So it's 5t. Make this a little bigger. Then we put a dot. And now we're done with all that. And then whatever the derivative of this is goes here. So that's how the chain, that's why part of the reason we call it a chain rule is it's this product of this chain of derivatives. And so the last piece is what's here. So what goes here? What am I going to write next? the number that's going to come out of my pen next. We're not done yet. Not quite there. So here's a game we can play. Let's walk up to our function. Yeah, you got it. 5 minus 4 t to the third. Done. But if we walk up to our function, the first thing we encounter is this parenthesis. That parenthesis is attached to the 1/2 power. We then took the derivative of the 1/2 power. And then we were done with that. Then we stepped inside and we kept walking. We took the derivative of the 3, but that was just 0 plus this. We encountered the log. The derivative of the log is 1 over whatever you have. We took care of that. Then we were down to this. The derivative of that is here, and then we were done. So there's the chain rule explained in another way. So the 1 on the top cancels the log. Yeah, so this, the derivative of log of whatever is 1 over whatever. So that's what we used. So this was the derivative of the log part. This was the derivative of the inside of that, and the derivative of the 1/2 was out here. Okay, so there's breaking down the chain rule. But I really just think about it from at the very beginning, we're just doing something to the 1/2, and then I just take it step by step. I don't think about it as a big blob. It's just one thing at a time. Okay, what about these next ones? These next ones are about rewriting and computing. So this is mostly about it. This is the same skill we've seen for a while, which is we need to realize that 5/3 is just a coefficient. We need to realize that 7/8 is just a coefficient. We need to realize the 6 is just a coefficient. But there's still a little more to do for this to be ready for calculus. The first term is ready for calculus. The second term actually is ready for calculus. I mean, you should be tempted to write this as t to the -1, but that's sort of a mistake because if you're thinking about integrals, you got to think about what we know. There's 3 rules. Here are those 3 rules. And you should sort of expect that there's 3 rules because there were 3 derivative rules, and there's going to be 3 integral rules going backwards. This one's the log. This one's 1 over a e to the at plus c. This is 1 over n plus 1 t to the n plus 1. So it's the direct reverse of our 3 derivative rules. And in this course, those are the only ones we cover. So put those up here. The derivative, there is a notation for it. I'm going to use it. The derivative is this. We'll talk about that notation more in chapter 14, but the derivative of log of t is 1 over t. The derivative of e to the at. Somebody's asking me to post all the derivative rules, but really these are them, the derivative and integral rules in this course. Can't you bring the t to the middle for 7/8? Let's see, what could we do? You gotta be careful with how you deal with fractions. So there's a question being asked about about this term. Let's play a little, run a little experiment here on the sides. So if you have 7 over 8t, let's play a little game here. So if I write 7/8 t, is that the same? And the way you could run the experiment is you could just pick a number. How about a 2? If I put a 2 here, and I put a 2 here, and this isn't quite what you were asking, but are the expressions the same? They got to be the same for all values. So this would be 7 over 16, and this would be 7/8 times 2, which would be 14/8. So if that t somehow escapes the denominator, we're in trouble. Some students find it helpful to think of it as a 1, like this. Well, that's actually what I did. But whatever's in the denominator should still be in the denominator at the end. Whatever's in the numerator should still be in the numerator. In calculus, we really would like to separate the numbers or the coefficients from the variables because all the rules don't have coefficients in them. And so it's an important first step, even though it's the same, it's an important first step to separate them in our head. Okay. There is one other thing I would like to do. So I'm not going to rewrite the 1 over t because it's already it's already one of the 3 rules. I am bothered by the third one because this does not look like this. So how do I rewrite the third one so it looks like e to the at? So everything we're doing is just trying to get it in a form that we can use our calculus. So let's go 7/8, which is better because the alternative is we have like 5,000 different rules for every possible number and situation. It would be too many. So rather than have a separate rule for when there's an e on the bottom and an e on the top and a coefficient, we just say we use our algebra to get it into one of those few rules we have. All right, that's the idea. Let me get this out of the way. Oh no, that's not what I want. What are you doing to me? Now it's shifted over. Okay, so now we're ready. I'm focused on that because this is the same skill you're using and derivatives and intervals, that rewriting skill. But now we're done. All 3 of those are ready to go. The calculus step is usually the easiest step because it's going to be 1/2 t squared minus 7/8 log of t. And then this is going to be minus 6/5 or 6 over -5 if you prefer, plus c. So there's kind of the answer in excruciating detail. Will this allow me to select this? Yay. So what's the best way to recognize the log quickly? I would just add in your memory banks, if you ever get to if you're integrating and you get t to the -1, that's a log. What's going to happen if you don't see it is you're going to try to use the other rule and you'll get 0 and you'll get a 0. And the moment that happens, you just say, oops, I should have used log. So if this happens, just go, oh, it's a log 1. Then you have it. So it's not the worst thing if you don't recognize it really. Like I said, if you go from here to here, you'll immediately see, oh, there's something off. And then you'll know it's a log. So it's not a big deal if you do that. But you just need to be aware that the log is a special power one. Okay, what about this one here? Again, we're working on the winter 2019 final. So this is the one I mean, you skipped this if you're looking at old finals. I mean, you should study the midterms first. I just was looking for something different. Okay, same game. We would like to rewrite this the way a calculus student would write it. So it's the integral from 1 to 25, 4 times 1 over the square root of x dx. So before I do integration or anything with the bounds, I'm going to become a calculus student. And what is this? We could say it in 2 steps if we want. This is 1 over x to the 1/2, which is the same as x to the negative 1/2. So now we're going to play the antiderivative, then plug in endpoints game. What I mean by that is, so when we have, these are called definite integrals, these things that mean area. I'm just gonna get rid of this for a second so I have some space. Here's what we do. Step 1, find an antiderivative. And we call that, we like to use capital F of x for lack of a better thing. Step 2, and we usually write this. We find an antiderivative. We write these bounds to say we've successfully found an antiderivative, and then we plug both the bounds in and subtract. So that's that fundamental theorem of calculus, all this connection. And so in this case, we haven't done the antiderivative step yet. And I find it very helpful to be careful with my notation. The moment I've done the antiderivative, I switch it to the other side to evaluate, which I think is a good convention that we do in math. Okay, so we still need to do the antiderivative. So we need to add 1 to the power, which makes it x to the positive 1/2. I added 1. And now I have a challenge. I've been talking too long. What is the number? You're not already asleep? Somebody said they're going to sleep, and I was like, how are you still awake? Okay, what is the number in front right here? Uh, so you're gonna flip the 1/2, which will be a 2, but there already was a 4 there, so this should be an 8. And then we're plugging in 1. Oops, I pushed a button. In 25. So that's this step. And then to finish the problem off, we need to plug in the 25. That's this. And plug in the 1. That's that. And subtract. That's what you were doing in 13.2. So let's play that game. Sometimes I like to do this just to remind myself, okay, I should be plugging in the 25 and plugging in. And honestly, the moment I want to plug in numbers, I'd rather write it as a square root because it makes more sense to me, but I'll leave it like that. So we're getting 8 times, I think that's 5 minus 8. So it is 32. I agree with Giovanni, who has already left. Okay. Where else do we want to go? So we've done some derivatives. We've done some definite integrals. There was a question long ago about point of inflection, but I may have already answered that. Anything else we'd like to do? Let me know in the chat. Could go a little longer since we kind of started late. And we'll definitely do more. We'll do these definitely gearing up for the final. So oh, good. Sorry. Let me go back here. We were looking at this question. How did it become 1/2 x squared? Which one am I looking at here? 5/3 Yes, this is recorded. So right here, this term, I got you, part B. Yeah, thanks for being here, Jude. So we have t. It's t to the first is how you should think about it. And the rule is you add 1 to the power and then divide by whatever number that is. So because it was a 1, this is going to become a 2 and a 2. That's where this came from. The 5/3 was already there because it was the coefficient. Does that make sense? Great. Any other things while we have this kind of open time? That's actually exam 1 sort of question. This is an exam 2 sort of idea. Yeah, I'll post it on the I'll put a link to it in the discussion board where I post those other videos. We haven't done a ton of problems, but we've talked about these ones. But I'd be happy to do 1 or 2 more. I have all the old midterms here. I have a couple of the old finals that I wrote, and I have all the homework. How's the homework going? Have we hammered the homework? These ones? Because we know we're going to have one question on the final where you have to do something like that, or that, or that. The very last question on the test. So would we be able to do such a thing? The integral from the start x to the end. This is the next video I'll be making in a second. And then we have the top function minus the bottom function. And here's the starting x. We do a lot of this in the regular calculus series, so I have to talk a lot about how we describe a region. Like if you're standing here and you start walking up, in that class I often have to talk about mowing the lawn. It's a lot to be said here. But for this class, we don't have quite as much to say of for any given x value, for any value from 1 to 3, you're between this and this, but this one's changing. If you were standing here, you'd go from there to there. The top is always 9, but the bottom's given by this formula. It turns out that gives you this area. And then once you have it, it's computation time. 9x minus 1/3 x cubed, and we get to do one of these definite intervals. Antiderivative, and now we're going to plug in a 3 everywhere, plug in a 1 everywhere, and we will be done. So that's the game you're going to be playing. The very last question on the test will be something just like this, where I give you a picture. And I say, what do you get? The numbers will come out pretty nice. This one, I'm just running it here, seeing how far I can go before I have to grab a calculator. 9 minus 1/3? That's not 9, that's 18. 9 plus 1/3, 9.3 repeated. 9 plus 1/3. WebAssign wants an exact answer, I assume. So you'd have to figure out how to, I think you can even type this into WebAssign and it accepts it. So I don't know that it's weird that it does, but we can get a common denominator, 27/3. 28/3, success. In the exam, I'll accept a decimal, that's fine. So does that make you think of any questions before we bug out here? Or are we asleep? I can't see what's on my screen. What I've been
What was the
giving away.
answer to the last question?
The random one I just threw up there. Let's
Yeah.
see what was that? It was a homework question. Now, I don't know that the numbers are the same for everybody, but I got 28/3. Is that what I got? Anybody else agree with that one?
Yeah, I got that.
I would not be, if I was doing this myself on the homework, I would take a little more time on this simplification. I don't trust myself. But if I did that right, then it's 25/3, 28/3. I don't know why when I print the homework, it looks like this. I've never figured this out. That's not what it looks like on your end. So let's see. Trying to think of any closing comments here. I do a lot of these in the videos that I'm about to post. They'll probably be out about a half an hour after I close this because I just need to edit them and post them. But derivative, this one has another derivative, integral with bounds. So we know our page 1 of our exam will be similar. We know we'll have something about concavity on page 2, something about finding plus C on page 3. All right. Any other things we want to see, particularly from an old exam or homework before we call it a night? Thanks for joining me. Like I said, we'll be doing a couple of these to gear up for the final. Probably on the Monday of finals week in the evening and maybe the Wednesday of finals week. We'll also have review sessions in class the week before finals. All right, thanks for being here. Wonderful.
Thank
Keep
you.
asking. Yeah, thanks for coming. Keep asking questions in the lab. Great.
Thank you.
Yep, thank you, thank you. Good, let's see, how do I close this thing out? More. Find the button. Close that, close this. Stop share and